Algebra 2, Chapter 12, Section 4, Long-Run Behavior of Polynomial Functions. When x is much smaller than or much bigger than 0, a polynomial function is dominated by its leading term. So if we were to graph a polynomial function where the input axis is very big, what if we went from minus 1,000 to 1,000? Then the leading term will dominate the long-run behavior, whatever that is. If it's x to the fourth, we'll have the shape of x to the fourth, no matter what other stuff is in the polynomial. If it was 300x cubed minus 200x plus 100, the shape will be roughly x to the fourth. And the more bigger we make, the further away from 0 we make these numbers that are the input side, the more and more it'll become shaped like the leading term. Therefore, the leading term determines the long-run behavior of a polynomial. In other words, how it behaves when we get really far away from 0. When a graph is zoomed way out, as I'm pointing out, its shape will be that of the leading term, because that is the long-run behavior. So let me demonstrate this fact. So again, let's do some graphing. This will just be some rough graphing. So let's just use a couple axes. You'll have to kind of use your imagination a little bit too. So if we have a graph that looks like this, when x is close to 0, when we zoom out, let's pretend I can zoom out on the same graph. That's your imagination. When I zoom out, way out, we're going to have the shape of x cubed, because that's what's dominating. The leading term here is x cubed. Okay, so we can also think about this on a polynomial that up close looks like this. Red line. When we zoom way out, the x to the fourth, which is in this polynomial, will dominate. So let's draw that in green. So when we zoom way out, we'll have a graph that looks like x to the fourth. Okay? That's the principle behind the long-run behavior. The leading term will dominate. And if the leading term has something multiplied by it, that'll be included in the shape. So for instance, especially important is if it's negative. What if our zoomed in polynomial looked a lot like this? Here we have a negative x to the fourth as our leading term, and then this shape opens downward. So our zoomed way out is going to look like, when I say way out, I mean way out. Like if we make it 10,000, and this was 4 was 1. This looks like a spaghetti mess, but hopefully you're getting the idea. So that we can use this long-run behavior to help us as we analyze polynomial functions from their graphs. For instance, suppose we need to find the polynomial function for this graph in blue. Well, the overall shape of this graph is up and up, so we'll have an even power. That'll be our long-run behavior. In fact, we can zoom ahead here a slide. And here's what the long-run behavior is going to look like for that polynomial. You can see when I zoom way out, even just to x is minus 30 and 30, I get millions of output values. My output values are in the millions, and the shape is very much looks like x to the fourth or x to the sixth. And if we look at the number of zeros here, 1, 2, and this looks like 3/4, it's probably going to be x to the fourth. So let's find a possible formula. So we first look at our zeros. Looks like we have zeros at minus 4, 1, and this looks like 1.5. Now this is a simple 0 here. So this is not going to be x to the fourth, because there's multiple zeros here. Look, this one hits the graph and bounces. This looks like x squared locally, so this is going to be a double 0, at least. And here we have a 0 where we come close to the axis, touch it, and go back down. So this looks like a triple 0. This looks like x cubed, not like a line locally. So we're actually going to have 6 different zeros here. So we need to now consider these zeros to write a possible formula. X plus 4, because it's negative 4. Double means it would be squared. X plus 1, because it's negative 1. Cubed, because it's triple 0. And then we have a simple at x minus 1.5 times some constant equals 0. That's our polynomial. Now, why did I write this constant? Because we need to figure out what this constant would be to get the possible formula, because we know the y-intercept. Okay, so we need to find what this should be to make the y-intercept negative 1. So the y-intercept is negative 1. And the y-intercept is going to be when the polynomial's input is 0. So when x is 0. So when x is 0, we would have 0 plus 4 is 4. 0 plus 1 is 1. 0 minus 1.5 is minus 1.5 equals 0. No. What we're trying to find is k. So equals minus 1, because that's the y-intercept. So the constant term, k times 0 plus 4 squared times 0 plus 1 cubed times 0 minus 1.5 is going to equal negative 1 in order to match the graph. Now we need to solve. We could write this too, by the way. This is our polynomial function of x. So what we're trying to find is when we put in 0, we know the output should be negative 1. So we put in 0 here to make this. And we know the output should be negative 1. We could do this with any point that's not 0 on the graph. If it's 0, we've already built in that information here, so that won't tell us more. But if we knew this point, for instance, we could use this point for finding the answer. And why is that important? Because if you have a 0 at the y-intercept, you're not going to be able to find k from the y-intercept. In this example, we have the 0. The y-intercept is negative 1, so we can use it, and it's faster, so I'm using it instead of some other point in the graph. But we could use any point. So using our calculator, we take 4 squared times 1 cubed is 1 times negative 1.5 and get negative 24. So negative 1 equals k, negative 24k. So k has to be 1/24. So our possible formula is 1/24 x plus 4 squared. And why is it only possible x plus 1 cubed? Because we guessed at that this was double. What if this was quadruple 0? What if this was to the 5th? But this will fit the shape very well, so this is a good possible guess for our polynomial formula for this graph. And again, the long-run behavior of that graph I showed you earlier looks just like x to the 6th. Very similar. You can see, like around 10, the graph is slightly different on the left versus the right. And that's because we're closer to 0, where the details do matter. But the further away from 0 we get, the more and more this shape becomes like x to the 6th. And that's the long-run behavior. Because we have, and really it's going to be 1/24 x to the 6th for this polynomial. Because that's our constant term. So if you were to, and we could even try this, we could find a point that's really close in the graph. Let's try 25 right here. Let's see how close we get just by eyeballing it. Somewhere around here. So if we put in 25 for x to this equation, we should get something that's close to 20 million. If our theories are all correct. So let's verify that a little bit. So if we take, let's see here, 25 and put that to the 6th power and divide by 24, we get about 10 million. So maybe we didn't trace this very well. Although 10 million looks like it's right here, and that looks like it's not 24. But again, we're approximating. This is an approximation. This long-run behavior is not exact. It's an approximation. The further away from 0 we get, the closer we get to the actual value. So if we were to put in to this equation the whole thing, 24, we would get the exact answer, 24 plus 4 squared times 24. Why am I doing 24? It was 25. 25 plus 4 squared times 26 cubed. 25 plus 1 is 26. Plus 25 minus 1.5, not plus, times. And then divided by 24 gives us 14.4 million. So you can see my tracing wasn't great. 14.4 million would be the actual point at which it goes to 25 here. So if we had a ruler, we could do a better job of looking at the graph. And how close is that to our estimate? Well, let's try it. So 25, again, 25 to the 6th over 24 is 10.1 million. So we're 4 million off. But again, like I said, the further away we get from 0, the closer and closer our leading term will be to dominating and being the long-run behavior. Consider the polynomial q of x is 3x to the 6th minus 2x to the 5th plus 4x squared minus 1a. What does the leading term tell us about the graph? The leading term tells us that the long-run behavior is 3x to the 6th. So the graph opens up because it's positive and is shaped kind of like this when we zoom way out, similar to 3x to the 6th. B. What does the constant term tell us about the graph? Well, the constant term will tell us the y-intercept. So it tells us that the y-intercept is -1. And C, what do the answers tell us about the number of solutions to q of x equals 0? So remember that there has to be at least 6, there has to be at most 6, just from the degree. There has to be at least 0 because it's even. But let's do better than that. So we know it opens up, and we know the y-intercept is -1, which means that here, close in, the graph must go below and at some point come back up. So there has to be at least 2 crossings of the x-axis. So there has to be at least 2 and at most 6. So there's at most 6 and at least 2 solutions. 6 coming from the degree, and the 2 coming from the fact that we opened up, but we had a negative y-intercept, so we had to cross somewhere twice.